Hello dear students, welcome to Pen and Paper Chemistry on YouTube.
Hello dear students, welcome to
Pen and Paper Chemistry.
part 16, Thermodynamics. There are 15 videos before this which deal with the basics and which deal with the basic terminology of entropy, enthalpy and so on. Please get the basics right before you advance with this video. Today we shall be talking about another thermodynamic quantity called as Gibbs energy. Now what is this Gibbs energy? What was the need for it? We did in the second law of thermodynamics, delta S total is delta S of the system plus delta S of the surroundings. That means the total entropy change is given by the change in entropy of the system and the change in the entropy of the surroundings. And we also gave three conditions where we said that the total entropy has to increase for a process to be spontaneous or to be feasible. That means for a process to take place on its own or by initiation, we need the delta S total to be greater than 0. If it is less than 0, the process will proceed in the reverse direction. And if it is equal to 0, then the process is in equilibrium. Picking up from where we left earlier, we also know that delta S is given by Q reversible upon T, that is the temperature in Kelvin scale. This we had equated to delta H upon T because most of the processes are carried out at constant pressure. Multiplying this equation by T on both sides, we have T delta S total is T delta S system plus T delta S surroundings. Now, why am I doing this? Why are we multiplying with T all of a sudden? Here, we need to understand that we are talking about the change in entropy of the surrounding. Now, measuring change in entropy of the surrounding is not an easy task. So, we need to get our physical quantities in terms of the system, which is much more easily measurable. Now, delta S of the system would be given by delta H of the system divided by the temperature at which the process is carried out. Similarly, for the surrounding also it will be given by this. But we also know that the heat lost by the system is equals to the heat gained by the surrounding or vice versa. So if one is positive, the other becomes negative. T delta S total is T delta S of the system, and instead of T delta S of the surrounding, I can also write it as the negative change in enthalpy of the system. Delta H of the surrounding is the same as negative delta H of the system. So here we can write the signs interchangeably as well. You have to remember that if one is gaining, the other is losing. Taking the negative sign, changing the sign, minus T delta S total is minus T delta S system plus delta HS. Now, why did we do this step as well? For this, we need to relate or we need to understand one more factor which was called as available energy by a scientist known as Gibbs. He gave the relation between enthalpy and entropy, saying that G connects the enthalpy and entropy of a system by the relation G is equals to H minus Ts. H, depending on the state of the system, we have G1 is H1 minus Ts1. This is in state 1, the enthalpy and the entropy of the system when the process is carried out at constant temperature. G2, that is when there is a change in enthalpy, you either provided heat or the system loses it. There's a change in the entropy of the system, but again the process is carried out at constant T. Now, if you notice over here, at state 2, it will be G2 is equals to H2 minus Ts2. Subtract G2 minus G1 is equals to H2 minus H1 minus, we again take T common from here, S2 minus S1. So change in Gibbs energy is delta H, change in enthalpy, minus T delta S. We had an equation from here. We have derived another equation. 2 minus T delta S minus T delta S. Delta H minus T delta S total is equals to delta G. So drawing an equivalence between the two equations, we have the mathematical value of delta G defined as minus T delta S total. So it is a measure of the maximum useful work obtainable from the system. What is G? This G was initially named as, of course, as I said earlier, the available energy or the available work. It was later called as Gibbs free energy after the name of the chemist who gave this concept. But since this is not really talking only about energy, because if you notice we have G as H and S as a combination of both. So it was considered more apt to call it as Gibbs energy, and later on they also proposed that we call it as Gibbs function. So if you see any of these terms, please don't get confused as to if they are referring to different physical quantity. They are all the same. What does delta G give us? Let us suppose we are carrying out a process where we talk about the electrolysis of water, acidulated water, giving us hydrogen and oxygen. Now what will happen is, because the gases are being released over here, we have liquid form of the water, we have hydrogen as a gas, oxygen as a gas. Now these are being released at the cathode and the anode. The gas, because it is produced, it will cause the system to expand. Expansion is PV work. That is what we have been talking about all the while when we said W is equals to minus P external into delta V or other expressions that we gave. Now in this process of electrolysis, we have got two products as well. Those are hydrogen and oxygen, which are not being measured in terms of the W, the thermodynamic W that we spoke about. The delta G that we are calculating over here, the fall in delta G, that is negative delta G, is a measure of this work that we are obtaining from a system. It is the work other than the work of expansion or contraction. So we say it is a measure of the maximum useful work obtainable from the system. What is a measure? The fall in Gibbs free energy. Or we say it is the non-expansion work. For our numericals, we shall be just using the expression delta G is equals to delta H minus T delta S. Now, if you notice over here, again I repeat, it is connecting H and S. We had done according to the first law of thermodynamics, saying that energy of the universe remains constant. We had given according to the second law of thermodynamics that for an irreversible process, the entropy tends to increase. Now, there are a lot of processes where we know that there is an absorption of energy, but they are quite spontaneous, right? There are a lot of processes where we see that the entropy is not increasing, but the process continues to take place. For example, we talk about substances existing as solid, liquid, gas. Now, if the systems were tending towards maximum entropy, the blackboard, the duster, the chalk, the pen, everything should slowly tend towards liquid state or gaseous state, because that's where maximum entropy lies. And secondly, when we talked about entropy as one of the factors, as one of the deciding factors, we had to take the entropy of the surrounding also into consideration. But if you see this expression, 1, it is connecting enthalpy and entropy together. 2, it is doing away with the measurement of the entropy change of the surroundings for us. So it is connecting the thermodynamic quantities of the system alone in order to measure its feasibility. How does it decide the feasibility? We will do in the next video. Here, delta G, since it's a physical quantity, it's a thermodynamic quantity, let us see its units. Delta G is delta H minus T delta S. How do you calculate delta H and delta S? Please see the previous videos for that. Now, the unit of delta H, if you see, the proper SI unit should be joule per mole. But in most of your numericals, you will come across the unit of delta H as kilojoule per mole. Delta S, change in entropy, that is heat upon temperature, and it's an extensive property, so joule per mole per Kelvin. Now, most of your numericals, you will see that entropy is actually given in joule per mole per Kelvin, while enthalpy is stated as kilojoule per mole. Please be very, very careful. That is why I have put it in red, because this is one mistake which we as teachers also tend to do many of the times. Multiplying kilojoule per mole per Kelvin by the temperature in Kelvin, we have the final unit of Gibbs energy as kilojoule per mole. Either you convert the joule per mole per Kelvin of entropy to kilojoule by dividing by 1000, or you convert the delta H kilojoule per mole to joule per mole by multiplying by 1000. In which case you will get the value, you will get the unit as joule per mole. But if you are taking both of them as kilojoule per mole, then the final unit of delta G will also be kilojoule per mole. Hope this clears the concept of Gibbs energy. Please watch out for the next video where we shall be discussing the feasibility of the process in terms of the change in Gibbs energy. Happy studying to all of you.
The only mission of this channel is to make learning chemistry easy and fun for all you students. With the help of the periodic table, the flowcharts, the graphs, diagrams, dealing with numericals, how to deal with numericals. And this can only happen when you keep a pen and notebook ready so that you can also take down notes for offline reference. There is no subscription to join the channel. There is no payment at all. Only request is to help spread a word about the channel by sharing it with friends, classmates, juniors, seniors, so that chemistry can be easy and fun for one and all. See you in the next video.